Hello, my name is Emma Goyette, and I've been working with my faculty advisor, Jerome Delhommelle, at the University of Massachusetts Lowell. Recently, I've been exploring motility-induced phase separation in active matter through simulations and exploring how changing different variables affects the results of these simulations. To briefly introduce the subject matter, our model builds on the Active Brownian Particles model developed and explored in the cited article. Using this model and knowledge about packing fractions and self-propulsion velocities, these variables were explored through non-equilibrium Brownian dynamic simulations. In regards to the packing fraction, it is known based on the given equation that it is an intensive variable dependent on the ratio of number of particles in the area. The self-propulsion velocity is represented by the shown equation. With a constant self propulsion velocity of zero point 0.1, different packing fractions were studied in order to gain an understanding on how the packing fraction affects the results of the simulations. Starting with a packing fraction of zero point 0.2, it can be observed that the particles look close to random noise with no real clusters forming. When moving on to a packing fraction of zero point 0.5, it can be seen that the system is trying to form clusters. This was an expected result as the packing fraction is not high enough to induce frozen stage and also not low enough to too much space for the particles to move in, which would limit the formation of MIPS. An additional important observation to be made is the decreasing area when the packing fraction increases, which aligns with the given equation. The last packing fraction observed was zero point 0.8, which is close to the packing fraction in which the frozen phase is expected. Starting at an even lower self-propulsion velocity than in the packing fraction study, the effect of self-propulsion velocity was studied with a constant packing fraction of zero point 0.5. The first graph pictured shows velocity of zero point 0.01. This graph does not exhibit the formation of clusters, but rather it is closer to the frozen phase despite being at a packing fraction of zero point 0.5. This makes sense as the particles would not be moving fast enough and they are moving slow so they cannot form clusters. The next graph is the one we explored before, which is the velocity of zero point 0.1. This graph seems to exhibit cluster formation. Moving on with a velocity of zero point 0.5, some clusters are still seen, but less than when the velocity was zero point 0.1. This makes sense as explored in the introduction. When the velocities are too high, particles will simply pass through each other. The last graph with a velocity of 1 shows what seems to be random movement as no significant clusters formed. With the packing fraction set constant to zero point 0.5, the graph of the potential energy versus time was explored at varying self-propulsion velocities. The first graph, having a self-propulsion velocity of zero point 0.01, exhibits the expected shape, with it starting to reach a plateau as the simulation concludes. As for the velocity of zero point 0.1, there are visible jumps, with one small one around 1,000 and a larger one after the 3,000 region. This shows that the particles are still colliding, so things are still happening in the simulation. One important observation to make is that the potential energy values go up as the velocity increases. This reflects when there are more clusters, there is more potential energy overall. And with that, we conclude our presentation. Thank you so much for listening.